My name is Dave Blei. I'm going to talk today about scaling and generalizing approximate Bayesian inference. Really, this is going to be kind of a tutorial about variational inference. And feel free to interrupt me if you have questions along the way. It's OK to not get through all my slides. So just to kind of situate the bigger field that this work is part of, here in Flatiron Institute, we have complicated data that we want to make sense of, right? And it might be that we have social science data, like a social network, or we have economics data, like people buying things. I don't really need this to point at those pictures. Or we have big collections of text data, or particularly here, we might have astrophysics data collected from space, and we want to understand what's going on in our data sets. That's a big problem. And so the field that this is part of is probabilistic machine learning, which also is the same as applied Bayesian statistics, where I want to build probability models that lead to statistical methods that help me connect my domain knowledge about space or about people or about other things to the data that I've collected, right? And so I kind of make assumptions and then analyze the data under those assumptions and domain knowledge. And our goal in this field is to make this methodology expressive, so we can express ourselves in the language of probability modeling, scalable, so we can handle large data sets, and easy to develop so that we don't have to do lots of work to do that. Okay, so here's just some examples. These are pictures from work in my own research group, because I have those pictures handy, of this kind of work. Like here, these are communities uncovered in a big collection of US patents that connect to each other. This is a population genetics analysis of 1 million people's gene sequences. This is a big analysis of a lot of fMRI data and what parts of the brain are active and how they're correlated when people are looking at different types of things. This is I've maybe shown you this slide before. This is a fancy econometrics model of people purchasing products at the grocery store, fit to hundreds of thousands of grocery trips. This was exciting. I was working with an economist because it showed us that crackers and cheese go well together. And so her Nobel Prize hopefully will be coming next year for that. This is some work that we did with David Hogg and other collaborators on understanding the dust map of the universe from astronomical data. It's a collaboration with Flatiron Institute. Okay, so I'm not going to talk about any of that stuff, just to give you a sense of what probabilistic machine learning applied Bayesian statistics is about. And all of those projects involve, in some sense, this probabilistic pipeline, where I take my assumptions about the world and my knowledge about the world and a question that I am asking, and I turn it into a probability model that involves observed data, shaded nodes, and hidden variables, unshaded nodes. Then I take my probability model and the data we collected, say the astrophysics data, and I use it to uncover the conditional distribution of the unshaded nodes given the shaded nodes, uncover the hidden patterns that I believe exist in the data. And then finally, I use those hidden patterns to form predictions and interpret my model and the world. And I like this picture. It might seem a little vacuous, but I like it because it really cleanly separates these activities. Making assumptions and writing models down, taking data and our model and doing some calculation of the hidden quantities given the observed quantities, and then using that calculation to do something. Okay, and this makes it easy, or makes it easier, to collaborate with domain experts when you are trying to understand a specific data set and answer a specific question. Now, today's talk is about posterior inference. This is the key algorithmic problem. This is the problem of how do I discover the patterns once I have my model in hand and my data in hand. And this answers the question, what does the model I made say about the data I collected? And what I want to talk about today is how to do that in a scalable way and in a general way. By scalable, I mean with massive data sets. And by general, I mean with a big, what's the word I'm thinking of? With many different types of models, no matter how difficult the posterior might be, to be able to do that easily. OK, so that's the main idea behind today's talk. So just for some background and to set up some notation, in probabilistic machine learning and applied Bayesian statistics, we work with probability models. And a probability model is a joint distribution of hidden variables z and observations x. Okay, so if you're in some kind of standard setup, your hidden variables might be the unknown parameters, and x is the data you observed. Okay, and we set that up in a probability model into a joint distribution p of z comma x. Now, inference in applied Bayesian statistics is about the unknowns happens through the posterior distribution, which I think you've probably already heard about in FWAM, which is the conditional distribution of the hidden variables given the observations. Okay, and so I'm not a crazy religious Bayesian or anything, but we are going to adopt this framework to make inferences about unknowns through the joint distribution of hidden and observed. Okay, and so the posterior is the probability of the hidden given the observed, right? And of course, that is the ratio of the joint and the marginal distribution of the observed. Again, there's no need to be Bayesian to calculate a posterior. It's funny because I made that remark, but I hadn't even known that that was going to be in the slide. I mean, I should have known. It's right there. My point is that these posteriors are sometimes useful regardless of why you're calculating it. And the problem is that for most interesting models that you might come up with at CCA or Q or N or B, the posterior is not tractable. And so we have to approximate that posterior distribution. So today we'll talk about variational inference as a general method or a general strategy for approximating those posterior distributions. And really, if you want to remember one slide from this talk, I hope it will be this slide. Okay, this describes variational inference in general, both the work that I'll talk about later, but also other work in variational inference that you might see in the research literature. So what's the idea? Now I think I will use the pointer. So the idea behind variational inference is to solve the problem of approximating this hard to calculate probability distribution with an optimization problem. And the idea is this. So the space on the slide here are all distributions over z, over the hidden variables. All right? And this one here, that's the actual posterior, the exact posterior that we care about, right? You might have your astrophysics model. X is all your stars data. Z is the dust map. You're interested in P of Z given X under your astrophysics model. And this is the posterior that you care about, P of Z given X. The problem is you can't calculate it efficiently. So what do you do with variational inference? You solve it with an optimization problem. You set up a family of distributions. That's this ellipse here. And it's called Q. Q of z, and it's parameterized by nu, which are called variational parameters. Okay, so every point in this ellipse is a different setting of nu, right? Those are indexing this distribution, and each one corresponds to a different distribution over z. Then what do? You optimize nu, the variational parameters, to be close to the exact posterior. All right? And by close, what we mean is to have small KL divergence, a measure of closeness between two distributions, of Q to P. Okay? And we'll talk about how you might change that at the end of the talk, but for now, this is the picture. Right? So I have my target, I have my variational family, I have my variational parameters, and my goal is to optimize those variational parameters using an optimization algorithm to minimize this KL divergence. That's it. Then, once you've found nu star, the KL minimizing distribution over z, you use it as a substitute for the exact posterior in whatever calculation you're making. Make pictures, make predictions, understand the universe, whatever it is. Okay? That's the idea. That's variational inference. So, as an example, let's just look at a very simple model, almost a boring model, which is a mixture of Gaussians. All right? In a mixture of Gaussians, as a generative process, we choose k different Gaussian locations. Then for each data point, we calculate a cluster assignment for that data point. That's zi, a number from 1 to k, and then calculate the data point, then draw the data point from a Gaussian whose mean corresponds to the cluster that we just drew. All right, so as a generative model, this is a useful way to think about probability models as a generative model of data. A mixture of Gaussians, after choosing the locations of the Gaussians for each data point, chooses a cluster at random, and then chooses the data point from the corresponding Gaussian whose mean is equal to that cluster assignment's mean. Okay? This relates closely to k-means, but you can think of this as a probability model and then calculate the posterior distribution of z and beta. The posterior distribution of z clusters the data. The posterior distribution of beta tells us where those clusters are. All right, so here is an example where, still need this pointer, so here is data that is actually drawn from a mixture of Gaussians. Okay, and now it's colored. These data points are colored by which cluster assignment they are attached to, but the model, of course, does not see that. Those are latent variables. And what we're going to do is do variational inference to estimate the posterior distribution of the clustering and the cluster locations for this data. And as we optimize those variational parameters, you can see this here. We're illustrating the posterior predictive distribution of a new data point. You can see that the posterior is getting better and better and more accurately representing the distribution of the data. All right. This is, we'll talk about what that is in a second, the evidence lower bound, but this is something like that KL divergence getting smaller and smaller as we optimize the variational parameters. Okay, this is the idea. You can contrast this to something like MCMC, which I think you heard about this morning, where we're building a sampler, right? In MCMC, I have a target posterior, and what I do is I build a sampler whose stationary distribution is equal to that target posterior. Here we're solving the same problem, approximating the posterior, but just in a different way with optimization, taking a family of distributions and optimizing its parameters to be close to the exact posterior. Okay? Any questions about this basic stuff? Great. It's just to, oh yeah, please.
So if the exact posterior is unknown, how do you calculate anything with respect to it?
That's a great question. So, and also it shows that you're paying attention. So right, here I have this KL divergence. My goal is to calculate P of z given x, and my objective function involves P of z given x. And so what's going to happen is we're going to have this other objective function called the evidence lower bound that is equivalent to this plus an additive constant. So optimizing the evidence lower bound is going to be equal to this. We'll see that in a bit. It's worth stepping back just for a second and talking a little bit about the history of this idea. So variational inference adapts ideas from statistical physics to probabilistic inference. And one of the earliest papers that does this is this paper by Peterson and Anderson from 1987, which fits a neural network with mean field methods. And the kind of in machine learning, this idea progressed in two threads. In one, in the 1990s, Mike Jordan and Tommy Yakula and Lawrence Saul, sitting in the back, one of the pioneers of this idea, and Zubin Garamani generalized this paper by Peterson and Anderson to many models and developed this idea, although it's weird to be describing this history in front of Lawrence, who was part of it. Is that accurate, Lawrence? Yes. Not that it's weird, but that, yeah. What's that? Weird and accurate. Yes, weird and accurate, yeah. What Mike told me is that Lawrence showed Mike this paper, and that's how it all started. Anyway, in parallel, or I don't know how in parallel it was, because everybody knew each other, Jeff Hinton and Van Camp developed mean field methods for neural networks and for mixtures of experts and for HMMs and for more neural networks. And so this kind of these two ideas were happening in parallel, and also everybody was talking to each other in terms of using this idea of variational inference to approximate difficult to calculate probability distributions. Okay, so today, what I want to talk about, and as much time as we might have, is that stochastic optimization makes variational inference better. All right, so here we're saying that variational inference is an optimization problem, and stochastic optimization helps us do two things with variational inference. One, scale it up to very large data sets, and two, generalize it to a very wide class of models. Okay, so I'll start by discussing how to scale it up. So how can we scale up variational inference to very large data sets? I showed you the mixture of Gaussians as an example model, but let's define, to do this, a general class of models. I call them conditionally conjugate models. And the idea here is that I have observations x1 through n. I have then two different types of latent variables. Local latent variables are called z, and there's one for each data point. And global latent variables are called beta, which help govern all the data points. Okay? Usually we might call global latent variables parameters. Okay? In this model, the ith data point, xi, only depends on its local latent variable and the global latent variables. All right? And so this graphical model corresponds to this factorized joint distribution, where I choose beta from a prior, and then conditionally independently, I choose the local latent variable and the observation given beta. Clear? Our goal is to calculate the distribution of beta and z given x. Yeah? You have a question? Okay. Good. So that's a model, but we're going to put some constraints on it. So just some jargon, the complete conditional is the distribution of a latent variable given the observations and the other latent variables. All right? And so, for example, this might be a better way to point. There are two types of latent variables in this model, beta and z, and the complete conditional of beta is the distribution of beta given all the z's and the x's. Notice it's different from the posterior. This is the posterior, p of beta given x, right? But here I'm also conditioning on this local structure. Okay? And we're going to assume that each complete conditional is in an exponential family. If you know what an exponential family is, that's great. If you don't, it's a general class of distributions that encompasses things like Gaussians and Dirichlet's and Poissons and gammas and so on. Okay, most things you know about. Okay, so we assume that p of beta given z and x is in the exponential family, and we assume that the complete conditional of each z is also in an exponential family, and that complete conditional, because of conditional independencies, is going to simplify. It only depends on its data point xi and beta, the global latent variable, and that's also in an exponential family. Notice the parameters of these exponential families, eta g and eta l, depend, of course, on what I'm conditioning on, as they would in a conditional distribution. Okay, this is the form of the exponential family, but again, we don't need to worry about it. Okay, so with those two assumptions, this class actually describes a lot of different models from the research literature. Bayesian mixture models like I just showed you, some time series models, factorial models like factorial mixtures, matrix factorization models, stochastic block models of communities, mixed membership models like topic models and some variants of topic models, some multi-level regression models, many, many models can be written simply as global variables, local variables, and observations. And certain realizations of these models have this property that the complete conditionals are in the exponential family. Okay, so now with that setup, we want to minimize the KL divergence between q of beta and z and the posterior p of beta and z given x. Okay, so now to your question. The KL is intractable, right? Because it involves this posterior that we can't calculate. So in variational inference, we optimize something called the evidence lower bound instead, which is also called the elbow, right? The evidence lower bound is a lower bound on the log marginal, which is the problematic term in the posterior. But more importantly, maximizing the elbow is equivalent to minimizing the KL. Okay, so it's equal to the KL up to an additive constant. So when we, or the negative KL. So when we maximize it, it's like we minimize the KL. All right, and there's the elbow up there. Oh, that's okay. The elbow has two terms. So you'll see, I'm going to point. The elbow is a function of the variational parameters, and it has two terms. Both are expectations with respect to q, the variational distribution. So this expectation depends on the variational parameters too. The first term is the log joint, the log of p of beta, z, and x, plus the entropy of q, which is minus the expectation of log q. Okay? Those are the two terms of the elbow. And it does not involve the posterior explicitly, but like I said, this is equal to the KL divergence to the posterior up to an additive constant. In fact, up to log p of x being the constant. Intuitively, you can look at this and see that it's kind of trading off two terms. So just to be clear, we're optimizing the elbow with respect to the variational parameters nu. So we're optimizing it with respect to this distribution q. Now the first term, if you just stare at the first term, it prefers q to place all of its mass on the map estimate, right? What is the what maximizes expectation under Q of the log joint? Well, it's going to be the Q distribution that puts all of its mass on whatever realizations of the latent variables maximize the log joint, and that's the map estimate. Okay, so the first term, if we only had the first term, Q, the optimal Q would be a delta mass at the map estimate of the latent variables. The second term, though, is the entropy, and that encourages Q to be diffuse, right? The second term says I want more entropic Qs, and so that says, well, a delta mass is not a good idea. I want to spread it out somehow. Now, these are just intuitions. Again, maximizing this objective function minimizes that KL divergence, which is reasonable. Charlie.
So to compute this, you have to know which latent variables go with which observation.
So yes, you don't know what the values of the latent variables are, but that's right. You know that there is a z for every x, and you know which z goes with which x. Yep. Yeah.
Is it the case that if P is in the family Q, the Q that is equal to P always optimizes this?
Yes.
Or are there other, degenerate situations where you get even better fits from some weird corner of the
No,
space?
it is the case. Right, we're optimizing this relative to Q being within the variational family. If the variational family was all distributions over z and beta, then the optimal, I guess I would have to think about if it's the unique optimal, but I think it is. The optimal is exactly the posterior. Yep, and that is an interesting way of writing down what the posterior is. It's sometimes called the variational representation of the posterior, and it's old. It's like this guy Arnold Zellner wrote about that in the 80s, for example. Yeah. Right. In fact, right. And so, but of course you can't do that because we can't calculate the posterior. So the idea is that we're simplifying Q. But that's a good sanity check. One caveat is that the elbow is not convex. So we're going to optimize this non-convex function. But it's machine learning, so we don't mind. Okay. All right. We're almost done totally specifying a problem that we can implement on our computer. But we haven't yet said what Q is. Okay, so the form of Q defines what's called the variational family, this set of distributions indexed by nu. And today we're going to be working with the mean field family or factorized family. Right, so Q of beta and z in a mean field family says that every variable is independent and governed by its own variational parameter. So beta is governed by variational parameter lambda, and each zi is governed by its own variational parameter phi. So to Charlie's point, each data point has its own local latent variable attached to it, and that local latent variable has its own variational parameter phi. So if you have 10 million data points, then data point 52 has a variational parameter for its local variable. Data point 9,620 has its own variational parameter for its local variable. So this is a lot of parameters. We're going to require, but it's also going to be optimal, that each factor is in the same family as the model's complete conditional. Okay, so here's P of beta given z and x. It's in an exponential family, like a Gaussian, with some parameter that depends on z and x. That means that Q of beta is also going to be a Gaussian, and it's going to have free parameters lambda. Okay? So the recipe is write down your model, write down the complete conditional, see what exponential families they're in, and then set your variational family to be fully factorized, but with factors in the same family as the complete conditionals. Okay? Graphically, it looks like this. Here's our model. Here's a mean field family with variational parameters. Everything is independent of each other. But what we're going to do is optimize the elbow. We're going to find the setting of this family that is close in KL divergence to the posterior here. Okay, so now we can fully specify the elbow. It's a function of lambda and all the phis. And again, it's these two terms. And kind of a classical approach to optimizing the elbow, now classical, is to do what's called CABI, coordinate ascent variational inference. And what that does is you march down all of your variational parameters one at a time, holding all the other ones fixed, and optimize each one. So I optimize phi1, phi2, dot, 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 to phi 10 million. Then I optimize lambda and repeat over and over again. Okay? And it turns out when you make these exponential family assumptions, or they're not assumptions, when you constrain your models to have these exponential families as complete conditionals, that those coordinate updates have a very nice form where the optimal lambda is the expectation of the parameter of the complete conditional of the global exponential family, of the global complete conditional. If you like exponential families, this is the natural parameter. And it's the expectation of this parameter under the variational distribution. But because of the mean field assumption, because of the fact we're working with a factorized variational family, this expectation is only going to depend on the local variable's variational parameters, phi. And so the right-hand side contains nothing that's on the left-hand side. Okay? It's a perfectly good coordinate update. And similarly for phi I. Phi i's coordinate update is the expectation of the parameter to the complete conditional of the local latent variable. And it only depends on the global latent variable, this expectation. So it only depends on lambda. All right, so you march down like this. And iteratively updating each parameter. Notice the relationship to Gibbs sampling. I don't know if you talked about Gibbs sampling this morning, but in Gibbs sampling, what do? We iteratively sample from these complete conditionals. That defines a Markov chain whose stationary distribution is the posterior that we care about. Here, we're doing something kind of like that, but iteratively setting these free parameters equal to expectations of the parameter of the complete conditional. Okay, but it's kind of spiritually very similar to Gibbs sampling. Okay, here it is as an algorithm. I just described the algorithm, so I won't go through this. And this is how we got this picture. All right, so what are we doing? Remember, we have our data, and each data point is associated with a local latent variable, which is the unknown mixture assignment of that data point, cluster assignment, sorry. And then the global latent variables are the locations of the mixture. And what do we do in each iteration of variational inference? We update each of these data points has a distribution of its cluster assignment attached to it. We update all those distributions for all the data. Then we update where we think the mixtures are. Then we do that again and again and again. And that's how we run variational inference for this mixture model. Yeah, Charlie.
So the latent variable for each data point is the cluster that it belongs to?
In the mixture model, yes. That's the local latent variable. In the mixture model, the local latent variable is the cluster, and the global latent variables are the locations of the mixture components.
There's only a finite number of clusters.
Yes, that's right.
Do you know how many ants in this?
In this example, you do know. Yeah, but this is just a tutorial example. And you could do something fancy like Bayesian nonparametrics, or you could try to learn K in some other way. There's whole decades of research on learning K. I wish there weren't. Yeah. Yeah.
How sensitive is the optimizer to the warmness parameter of your starting distribution?
Is
Is it logarithmic?
Did you say is it logarithmic?
Yeah, and that warmness parameter, the relative density of the starting distribution with respect to your target.
Well, I was going to give you a much less precise answer, which was just to say it's really sensitive.
Okay.
How it begins, but it sounds, but understanding something about that would be really interesting. I think that there's not a lot of work on how to initialize variational inference. Right? There are things that work in practice. For example, with mixture modeling, you want something kind of diffuse that encompasses the data, but is not so rigid as to kind of pre-commit you to some kind of clustering to give you freedom, but kind of making those intuitions more rigorous. I don't know of any work that does that. Yeah.
Thanks.
So you get an example by similar from mixture of Gaussian.
Yeah.
How would you, for example, introduce beta in that scheme?
Beta?
Yeah, the stochastic part.
Oh yeah, we're going to get to that next. Yeah, yeah. So how to do stochastic optimization, right? Right, what's the issue? The issue is that this kind of classical CAVI is inefficient because, like I said, if you have 10 million data points, you start out with no idea where the mixture components are, and you painstakingly go through every data point and update your idea of where it should cluster, under this garbage mixture components, and then update the mixture components. This is very inefficient. At more generally, because we're doing local computation for each data point and then aggregating those computations to re-estimate the global variational parameters and repeating. And so stochastic variational inference scales up the idea of variational inference to very large data sets. Okay, and the format of stochastic variational inference is like this. I'm going to have a massive data set. I'm going to subsample my data. I'm going to do something, infer the local structure for that subsample. In other words, do local variational inference for the subsample. And then I'm going to use that small local computation to update the global variational parameters. Right? And you can see that this is going to be more efficient, although I haven't shown you why it would work, because rather than going through the entire data set to infer the local variational parameters, I just need to do it on a subsample. Yeah.
Can I just think of that as the Gibbs step, but with random coordinate axes and lots more global updates thrown in?
Yeah, that's right. It would, if we were to do this in a Gibbs sampler, we would take a subset of the data, we would sample their clusters, and then we would sample the mixture locations, and then we take another subsample and subsample their clusters. So this is, I hadn't thought of that connection. This is like a way of reordering the Gibbs steps in that sense. Yep.
Okay,
yeah.
cool.
Interesting. But how will we get there? How do we derive that that is a good algorithm? We're going to use stochastic optimization. All right, so that's Herb Robbins. He was an amazing statistician, invented bandits, stochastic optimization, and empirical Bayes. And somehow I think he co-authored a book with Courant, but then it wasn't credited or something like that, or maybe it was. I don't know the details.
He did a lot of the work, and Courant didn't want to put his name on it, and then people yelled at Courant, and then he put his name on it.
Ah, okay. I knew it was some kind of story like that. Anyway, amazing guy, Herb Robbins. And you all know stochastic optimization if you've ever fit a neural net, right? Stochastic optimization is basically the idea that when I'm optimizing an objective function, if I have some cheap way of getting noisy gradients, something that sort of approximates the gradient with randomness, then I can follow those noisy gradients and still get to the top of the function or the bottom of the loss function. But I'm usually maximizing. Okay? So that's the idea. I can replace the hard to calculate gradient with a cheaper, noisy estimate of the gradient and still optimize my function effectively. That's what, and this idea is from 1951. It's pretty old. Now, this idea has really enabled modern machine learning, right? Why? I mean, this is not about variational inference anymore. Why do we have Google and all this stuff on the internet? Why can we fit recommendation systems to millions and millions of people's data? It's because of Robbins and Monroe. It's because of stochastic optimization. We set up an objective function and we optimize it with noisy gradients, right? And so Leon Botou really brought this idea into machine learning in the 90s. And this is scaled up neural nets, scaled up everything, won Nobel Prizes, et cetera. Okay? Herb Robbins. So how are we going to use this in the context of variational inference? We're going to use noisy gradients to update our variational parameters. So rather than doing a coordinate ascent scheme like we were doing, we're going to do a gradient ascent scheme where we're going to take the gradient of the elbow and follow the gradient. All right, so nu t plus 1 equals nu t plus some step size, rho t, times the gradient. But we're going to use noisy gradients. That's why there's a hat on the gradient. And in stochastic optimization, we have two requirements of the gradients. Well, really one requirement. One requirement is that it's cheap to calculate. If not, there's no point in using it. And the other is that it's unbiased, meaning that the expectation of my noisy realization of the gradient is equal to the actual gradient. Okay? Classical Robbins-Monroe also requires that the step size sequence follows the Robbins-Monroe conditions, which loosely say that I can get anywhere I need to be in the landscape of the objective function, but I'm not going to overshoot. I get more and more conservative as I continue the optimization path so that I can actually get to the top. But modern methods, again, I think probably many of you know this here in the room, ignore the Robbins-Monroe conditions and involve fancier adaptive step sizes like Atom or Adagrad or RMS prop or Poliak step sizes like Robert taught me by a lake. So this is the scheme we're going to work with to optimize the variational objective. So how do we do it? I need to tell you one more statistical thing about this conditionally conjugate setup. So the complete conditional of the global variable, remember P of beta given z and x is in an exponential family. And what it's going to look like, for it to be in an exponential family, it's going to have this form. Some hyperparameter alpha, which is a hyperparameter to the prior on beta, plus a sum over my data of some statistic of the local variable and the data point. Okay? If P of beta given z and x is in an exponential family, then the natural parameter of that exponential family will have this form. Okay? This is from the classical theory of conjugate priors. Now, what that means is that the coordinate ascent update, lambda star, remember it's equal to the expectation of eta sub g of z and x. That's going to equal alpha plus the sum I equals 1 to n of the expectation under phi I of this statistic of z and x. Okay? And now we've kind of zeroed in on what makes the algorithm expensive, right? Because I have to calculate this expectation for all my 10 million data points, this is going to be expensive to calculate. There's a third idea we need, which is the idea of the natural gradient. Okay, so Robbins-Monroe is pretty old, 1951, but there's this other idea of natural gradients from really from the 80s and 90s, which is about how to optimize parameters to probability distributions, right? And so kind of at a high level, the idea is this. The definition of a gradient somehow assumes that we're in the Euclidean space and we're getting infinitesimally small and we're looking at a direction of ascent, right? But in a probability distribution, a parameter of a probability distribution, if it's not Gaussian, marching 1 centimeter in one direction could lead to a huge change in the probability distribution, and marching 1 centimeter in another direction could lead to a very small change. And so what a natural gradient does, what information geometry does, which is the work of Amari, his lifelong work, is warps the space of landscapes of objective functions relative to probability parameters, warps that space so that we can define gradients more naturally, so that 1 centimeter walking each direction leads to the same difference in symmetrized KL divergence, even if you're optimizing the parameters of a gamma distribution or some other kind of distribution where there would otherwise be some kind of non-symmetric change in the distribution walking different directions. So that's what a natural gradient is. And it turns out that the natural gradient of the elbow has a very nice form. It is exactly the coordinate update minus the value of the parameter. Right? So the natural gradient of the elbow relative to the global variational parameter lambda is equal to the coordinate update minus lambda. The usual gradient does not have that nice form. Okay? And so with this, we can construct a very nice, cheap, noisy natural gradient. We sample from our data set at random, sample a data point at random, 1 to 10 million, and then calculate its local variational parameter, and then scale it up inside this formula for the natural gradient by n, right? And you can just see that the expectation of this noisy natural gradient because it's choosing a random data point, is going to be equal to the actual natural gradient. Make sense? Okay, so this, yeah.
Sorry, can I
Please.
ask a question?
Yeah.
Where did the derivatives go in the gradient? I sort of was expecting all of these eta parameters to have, like the FWAM or whatever is going to take derivatives of all of these things. And if you're going to do SGD, you need to take a derivative, and that would involve derivatives of these, like partials of these t functions or partials of the etas or something.
Right.
Where did that all go?
It went away.
I see. That's
Yeah.
scary. Yeah.
Yeah. So you should look in the paper, but exponential families are very nice because when you take, so the derivatives are hidden in here.
Yeah.
It's a fact about the exponential family that the gradient of the log normalizer is equal to the expectation of the sufficient statistics. Okay, so an exponential family, this is now,
That's the conjugate. It's something to do with conjugate primes again.
this is actually just about exponential families. So an exponential family is this is maybe, well, it's so much fun to talk about exponential families. Exponential family is p of x is proportional to x of, let me go to the board. This is a blackboard? Oh, okay. That's too much. I'm going to just go like this. Here we go. Okay, so here's an exponential family. Forget about h. It's p of z is proportional to x of some natural parameter eta, inner product with some function of z. It's called the sufficient statistic. Okay? And then a of eta is the normalizing constant. It's a function of the parameter, and this ensures that this distribution integrates to 1. Okay? Now, it's a fact that, and you can prove it, it's like a couple lines, that the derivative of a of eta is equal to the expectation of the sufficient statistic. Okay? And so, I'll show you to the paper. Whoops, I went too far. I'll show you the paper at some point, Alex. But this is where the derivative is that you're worried you're not seeing. Okay, good.
And this also looks a bit like a Legendre transform. Is there any connection to Legendre transform?
I don't know.
Okay, doesn't matter.
Good. Does somebody know? Okay. Great. So, but what's the point? The point is, this is good for stochastic optimization. Its expectation, it's unbiased. Its expectation is the exact natural gradient. And it's cheap. It only depends on the optimized parameters of one data point, right? Instead of marching through all my data and calculating phi star, I just pick one, calculate phi star, and then scale it up. Or I make a mini batch, right? This is where mini batching and things like that come in. All right, and so then here's stochastic variational inference. The input is my data and a model. I initialize lambda randomly. I set my step size appropriately. If I'm old-fashioned, I use Robbins-Monroe. If I'm modern, I use Polyak or Atom or RMS prop. I then sample a data point at random or a mini batch, calculate its local variational parameter. There it is. Set this intermediate global variational parameter. That's the coordinate update, lambda hat with just that data point, and then update with the gradient, which is what this step does, okay, which looks at a difference between the old lambda and this lambda hat. Okay, and that's that. So why is this good? So here's another model. This is latent Dirichlet allocation, a topic model, a model I worked on in my dissertation. And what this is a mixed membership models of document collections. So basically, I'll just be brief about this. It's like a mixture model, but now instead of clustering data points, I'm modeling document collections. And each document is a collection of words, and each document itself comes from a mixture model where the mixture components are distributions over words, but how often I see each mixture component changes from document to document. Okay? And so here's beta. These are distributions over words. Now, for each document, I choose a distribution over these distributions over words, which are called topics, distribution over topics. And then for each word in each document, I choose a topic from that distribution for this document, and then I choose the word from the corresponding topic like I would in a mixture model. All right? And this, now we have ChatGPT. We don't need LDA anymore, but this was a good way to extract topics from big collections of documents. Okay? This is called topic modeling. And maybe not totally replaced by ChatGPT, I don't know. Okay, so here's an example of topic modeling at work. We take in 1.8 million articles from the New York Times, and here are the mixture components attached to it. And you can see that even though it just looked at the text of the documents, it found these topics that are prevalent in the newspaper. Okay, but you can't fit a topic model with variational inference to 1 million articles quickly, right? And so this is why we like stochastic variational inference. So classical variational inference takes our 1.8 million articles from the New York Times, takes random topics that mean nothing, and painstakingly analyzes each document according to those topics that mean nothing, and then updates the topics. And here in this plot, we see how much computation we're doing at a log scale and how good the model is, where lower numbers are better. And so classical CAVI marches through all the documents one at a time and then updates the topics, gives you this value, right? Then does it again it's at the log scale, gives you this value. Again, this value, each time going through 1.8 million articles. But stochastic variational inference, and this picture really is a picture about stochastic optimization. You can see this picture about neural nets and regression and all kinds of things. Says, you know, I'm going to be iteratively updating my topics with noisy gradients as I sample them. And what you can see is that when you've done as much computation as one iteration of CAVI, you're in a much better spot. Okay, that's the idea. All right, this is how we were able to fit mixed membership stochastic block models to very large networks. This is how we were able to analyze large-scale human genomic data. And again, I showed you this conditionally conjugate model that captures many models, and now you could scale up all of these ideas, you could scale up variational inference for any of these models with this way of doing things. I should add that stochastic variational inference really looks a lot like work that was done much previously to it around scaling up the EM algorithm, and it's very closely related. So here's some of these, and one of the people like Neil and Hinton, and then Kape and Moulin proving that it worked. These are really the precursors to that idea. Oh boy. So I have 2 minutes left.
So we have 10 minutes.
Oh, okay.
Of that, yeah.
Okay, I'll just go quickly. When Lawrence Saul introduced variational inference to the world, if you wanted to work on variational inference, you had to write appendices like this. Right? This is an appendix from a paper I wrote on latent Dirichlet allocation. And it is in this appendix that I derived the variational inference algorithm for latent Dirichlet allocation. Right? But I was not special. Every paper back then had an appendix like this that derived the inference algorithm, maybe even a Gibbs sampling appendix. Right? And appendices are a bummer. And it's a problem because there's a lot of places where you can make a mistake. Right? And in fact, there's a mistake in my appendix. Okay. I won't show it to you, but it's in there. So, what's that?
Exercise for the reader.
Exercise for the reader, yeah. No, that's not true. That's not the point. The point is we don't want to write any more appendices. And so I don't want you to have to read my appendix or write an appendix of your own. And this is the idea behind black box variational inference. We want to develop a VI algorithm that we can easily use with any model that does not make exponential family requirements like we did in the previous part of the talk, and still lets us accommodate large data sets. Okay? That's the idea. I take my reusable variational families, any model at all, a big data set, plug it into a technique, and then out pops an approximation of the posterior. We maybe didn't name this well because black box makes it sound opaque, but anyway, that's the idea behind black box variational inference. All right, and many models do not satisfy the conditional conjugacy requirements of the last part of the talk, right? Including simple models like logistic regression, right? But also including things like sigmoid belief networks, some variants of topic models, some deep learning models, and so on. Okay. So I know I don't have very much time, so I'm just going to give you a really quick sketch of the main idea behind this way of doing things, and also tell you a little bit about how it's used. So the main idea is simple. Okay, here is the elbow that we already talked about, but I don't want to make any requirements on complete conditionals. So what I'm going to do is I'm going to write the elbow down as I'm going to write the gradient of the elbow down as an expectation. Okay, I'm going to figure out a way to do that. I'll show you two different ways of doing that. Then I'm going to take Monte Carlo estimates of that expectation, and I'm going to then follow those estimates using stochastic optimization. In other words, usually we think of stochastic optimization as being a way to overcome very large data sets. We subsample the data, that gives us noise, that gives us a noisy gradient, we follow that noisy gradient. Here we're saying, look, we have a gradient we can't calculate, but if we can write it as an expectation, we can get a noisy gradient by taking a Monte Carlo approximation of that expectation. And that's another way of getting a noisy gradient that we can also apply stochastic optimization to. We want to keep in mind what we call the black box criteria, that we should only need to sample from Q. That's something I can write down in a library and then reuse over and over again. Evaluate things about Q, same thing. And evaluate log P of beta, Z, and X. All right, so that is a requirement that I can evaluate the log joint of my model. For many models, you can, and in some sense, this is what it means to specify a model, although in fields like climate science and astrophysics and cryo-EM, there could be models where I can only sample from P of beta, Z, and X, and this does not apply to that. That's the realm of simulation-based inference. Okay, but these criteria, if we could satisfy them, let us perform approximate inference on many models. Okay, so there's two ways of writing the gradient as an expectation. Here's one which is called the score gradient. The gradient of the elbow is an expectation under Q of the product of these two terms. This one I call the instantaneous elbow, log P of X and Z minus Q of Z. And this is the score function, the gradient of log Q relative to the variational parameters. The literature is confusing because, well, I'll explain later. Okay, that's one way to do it. And we can use that method to perform variational inference, let me be clear, we can take Monte Carlo approximations of this gradient and then follow them. And that lets us do things like variational inference on complicated deep learning models like this one that does not satisfy conditional conjugacy. And then this is a standard table you need to have in every computer science talk that says that your method does better than everybody else's. But in this case, the point of this table is that we can make this table, and that we couldn't make that table easily if we had to derive appendices for each of those different types of models. There's another way of writing down the gradient of the elbow as a expectation, which is called the reparameterization gradient. This is what's used, for example, in what's called the variational autoencoder. And this is what let us build this fancy discrete choice model and this neuroscience model. But I wanted to make sure I mention this, that the reparameterization gradient in connection with STAN, with probabilistic programming, lets us implement variational inference for any STAN program. Okay? So it's important if you want to do probabilistic programming and really build a robust tool that can generalize to lots of different models, that your variational inference algorithm can generalize to lots of different models without any kind of hand-coded mathematical work. And so it's thanks to this idea of BBVI with reparameterization gradients that we can implement VI in STAN. Okay, so I'm over time, I realize, so I'm going to just stop and remind you of this picture, and that this picture also points to how to do research in variational inference, right? So you can expand the models that VI can handle. That's what we did with BBVI. You can expand the class of variational approximations. You can find new methods for optimizing the variational objective. Robert and Diana and Chirag and Lawrence and me and Charles have been working on that kind of weekly. You can explore alternative measures of closeness between distributions, so play with this KL divergence to try other objective functions. And you can ask theoretical questions about VI or about the initialization of VI and about optimization. So this is a nice picture to stare at if you need something to work on you can just look at it and work on one aspect of it. Okay, I'll stop there. Thanks very much. If you're interested.
So we have 5 more minutes for questions.
Yeah.
Regarding the KL objective, is there a philosophical reason why you choose one direction rather than the other? Is it just because it's more computationally convenient for the elbow?
So you asked if there's a philosophical reason?
Yeah.
Yeah. No. It's the second,
Okay.
your second intuition. It's easy to calculate because the expectation is relative to a distribution that we have our hands on.
Mm-hmm.
That said, there's all kinds of work. You know, it's kind of about where you place the approximation. You can imagine KLPQ and then work on approximating that expectation. And for example, there's something called expectation propagation. I don't know if it's still used that much, but that targets KLPQ. There is a very interesting paper, I forgot what it's called, by Jeremias Naubloch, and it's about define. You know, we talked earlier about how you can define the posterior variationally, and this objective function falls out of that definition, and it talks about how changing some of the ingredients of that definition of the posterior, in other words, changing your posterior, leads to different objective functions, and they might have different properties. That objective function, in some sense, defines what it means to be uncertain about your parameters in the face of data. So there's that has if you're interested in the philosophical reasons for it, that paper is a good place to look. Yeah, I thought it's a fascinating paper.
Thank you.
There's another question.
Awesome talk. How do you systematically control the asymptotic bias in the algorithm? I mean, what do you? I mean, how can you do that in a black box way?
That also suggests research that I'm not aware of anybody doing, right? So understanding the theoretical bias of variational inference is difficult. You know, with MCMC, we have theory that we know that the long-term sample from the Markov chain, if you know, my great-grandchildren could enjoy that sample, would be a sample from the posterior. But in variational inference, even if my great-grandchildren ran the optimization, they would still not know how far away they were, right? Because there is a gap between the actual optimized new star. Forget about local optima and all that other stuff. There's an actual gap here that we do not know. Though some of my students have done work on theoretical guarantees for variational inference asymptotically, like as you see more and more and more data. For example, you can imagine when the posterior concentrates, then mean field at some point kicks in as being a good idea, and then you get to the exact solution. But it's theoretical, right? It's under asymptotic data. And then I think there is some work maybe by Chao Gao at Yale about finite sample guarantees for variational inference, but I'm not quite sure. Is that right? Chao Gao's at Yale? No, he's at Chicago. Yeah.
So there's a lot of ways to take a single sample, estimate its gradient, and scale that will result in unbiased gradients.
Yes.
It doesn't have to be uniform sample by sample.
That's right. Yep.
And in most inference problems, there are some observations that are more informative than other observations. Are there ways to combine those facts and make the gradients that you're choosing not uniform, but instead concentrate on the informative observations? Scale them up less.
Yep,
so
of course.
Comes out in the wash in the right way.
Yep. So, right. Number one, yes, you're right. Like if you handed me a distribution over observations, I can turn that samples from that distribution into an unbiased gradient of this thing, right? Just by doing kind of IPW style importance reweighting. It's also true that if I have a big document collection and I'm fitting a topic model that if I have 25 documents about seals, then sampling all those seals documents is not going to do that much, but rather sampling a document that's far away is going to do more. And so, yes, again, it's a cool research idea to ask, how do I optimize that distribution over data points to accelerate optimization? Something that we've been working on, though we just have been working on it now, is in the context of CAVI. It's the same idea. It's kind of like in Gibbs sampling when you want, which observation should you sample next. In the context of CAVI, you can ask, which coordinate do I update next? And we're trying to think about Bayesian optimization solutions to that problem. So, but it's tricky because you're up against, as soon as I spend a lot of calculation to decide what data point I should sample next, I could have sampled many, many different data points and possibly gone to the same place. Yeah, that's a good question. And it's of course tantalizing, right? You feel like you could build a hash function of your data, and then anyway, who knows what you could do? Yeah.
1 second. Actually, we have to go to lunch. So if you have further questions, please feel free to talk to David, and let's thank him now. We'll be back in 1 hour.
Can I mention one more thing? Seeing Lawrence reminded me. I'm working on a book about these probabilistic machine learning ideas, and I'm interested in feedback about that book. So if you would like to read about this kind of thing, send me an email to my Columbia email address, and then I'll send you a table of contents, and you can read whatever you like. Yeah. Thanks.